K. So we want to find the equilibrium constant. So K here is our unknown. Based on the data table given, we're going to have to use the ghost equation to get delta G naught, and we're going to have to use summation to get delta H and delta S. So, first thing, let's get our delta H. So we've got products, 2 times negative 826 minus reactants, 4 times iron, which is 0, and 3 times oxygen, which is 0 because they're in their standard state. So we have negative 826 times 2. Negative 1652. And this is kilojoules per mole. For delta S, we have 2 times our iron oxide, which is 90, minus 4 times iron, which is 27, and 3 times oxygen, which is 205. So 2 times 90 minus 4 times 27 plus 3 times 205. And we have negative 543. But this is joules per Kelvin mole. So convert it to kilojoules. So now we can substitute into the ghost equation. So delta G equals delta H. Minus T, again we're at 25 degrees Celsius, which we know is 298 Kelvin, times negative 0.543 kilojoules per Kelvin mole. So our Kelvin cancels, and we have kilojoules per mole for both of them, so we can add those. So I've got negative 1652 minus 298 times negative 0.543. Oops, I never opened a parentheses, so I don't need to close them. And I got negative 1490. All right. So now I can actually use my Rate-Length equation. Delta G equals negative RT ln K. So I have negative 1490 kilojoules per mole, negative 8.3145 joules per mole Kelvin, times 298 Kelvin, times the natural log of K. So I have to have this in kilojoules. So if I make it negative 8.3145 times 10 to the minus 3, I'm now in kilojoules. Okay, so I'm going to divide both sides by R and T. So delta G divided by RT equals the natural log of K. So then that means take the opposite of natural log, which means it is e to the negative delta G over RT. Okay. So negative 1490 divided by negative 8.3145 times 10 to the minus 3, also divided by 298. Sorry about that. Another video was done finishing up. All right, so that gives us 601. So we have 601 equals the natural log of K, or e to the 601 power equals K. So second function natural log, 601, and we get an error because that's too big for the calculator. Just report it like this. Okay. We can also use this to calculate a phase change. At a phase change, we have an equilibrium between phases, so delta G naught is 0. So if we want to find the boiling point of this, delta G equals delta H minus T delta S. We want to find the boiling point, so we are solving for T. Delta G is 0. So you can do the algebra before or after you put numbers in. Okay, now remember, we've got kilojoules and joules. So go ahead and convert your joules to kilojoules. That makes it so much easier. So we've got negative 44 kilojoules equals negative T times 0.1188 kilojoules per Kelvin. So the negatives cancel out, and we have 44 divided by 0.1188. Oops. Clear out that last problem. 44 divided by 0.1188. And we get Need a bigger screen. 370. So we get a boiling point of 370 Kelvin. Now, that last calculation we had in the list, which was delta G equals negative NFE. That's electrochem, so we're not going to do any problems with that until we're in the electrochem chapter.